of cable sheath types in various environmental conditions. You see, for instance, metal plastic sheets with metallic tapes. You see plastic sheets only, plastic sheets with strength members, plastic sheets with embedded strength members with metallic tape, cable sheets with armoring. So you see how the choice of these different possible sheath types are acting on the different cable types which are used in the world. Aerial cables, you see that all those are applicable. A stands for a typical applied type. Underwater cables, and generally we have another construction. We usually don't have those plastic sheaths around that. Building is also a different application. Usually we have here plastic sheaths only, because inside the building we don't need to have such a high armoring of the cable construction, because there is not such a high forces working on a building cable. So again, I give you an overview of what is present in the market. We move then to structure of optical cables for specific installations. What time did we say that we would? 12:30. Okay. So far we have been looking to general cable constructions. The handbook indicates a couple of specific installation types. So here we see under 4.1 optical fiber cables for aerial applications. And here we can also refer to another document in ITU, recommendation L26. Another category of special cables is Marionized terrestrial cables. Also here we have a special document. These Maronized terrestrial cables are for shallow water applications and also in lakes, crossings, etc. If you really go to deep sea and ocean types of applications, there's a construction around submarine cables. Also here we have a recommendation G968. We can also have, and this is an application more for fiber to the home applications, maybe strange applications, that is an optical fiber cable in sewer duct applications. It's a strange environment, but these kinds of cables have been developed to make it more easy to install fiber to the home systems, in particular in large cities, where you have, of course, a sewer system already in place, and where you can place quite easily special cables, and then you have already large portion of your installation has already been done. You don't need to dig special holes in the ground in large cities, which is always a problem. You can use then the sewer duct system. And we have optical fiber cables for building constructions, multi-dwelling, fiber to the home constructions, in particular riser cables. So we will follow them one by one. And the first one is on aerial applications. Concerning the environmental aspects of aerial applications, water is a very important aspect. Water in the cable, of course, may frozen at low temperatures and cause a fiber crushing, which causes an increase of optical loss, and even in some very extreme situations cause fiber breakage. So it is an element to be taken care of. Another aspect of aerial cables is in overhead cable, the aspect of vibration. There is always a wind surrounding an aerial cable, and such a cable can start acting in vibration or even galloping. So the cable is going to move up and down under the influence of wind. This, of course, will add some additional strength and strain on the strength members, and of course we should design the cable in such a way that we do not cross a certain maximum limits in which the fiber could break in the end. A very significant aspect is the temperature variation. Certainly for aerial applications we see a large impact of temperature on the cable construction. Much more than, for instance, in duct or directly buried cables, where the temperature is much more smooth and not changing so much. In aerial cables, you will see a much heavier influence of the temperature on the cable construction. In particular, for applications in cold climates, so the Nordic countries, we see that snow loading and ice formation around the cable is also of particular importance, because it could increase the strain on the cable, causing optical loss and in some cases even fiber breakage. So also for the Nordic countries, those cables should have a very special design on this aspect. Metal-free aerial cables installed in high voltage power lines, a very easy application, of course. Many of those high voltage lines can be equipped also with optical fiber cables and units. Of course, these, they are susceptible for the influence of electric field. So the position of the cable at the minimum field strength is of importance, and the use of special cable sheaths and materials is important. So we see that each application, we see it also for the other applications, special environmental aspects are acting on the design of the cable. Any questions on aerial applications? If not, the cable construction is often 2 or 3 types. We have a type quite popular, the all dielectric self-supporting ADSS type of cable, in which the tensile elements are provided by non-metallic reinforcement. So, for instance, by means of aramid joints, glass fiber reinforcement materials, or equivalent dielectric strength members. So we don't have metallic strength members. And that's, of course, certainly an issue to reduce the impact of lightning on this kind of cables. Another construction is indicated over here, self-supporting cable. You see the sheath is including a metallic or a non-metallic bearing material, and we have a special strength member on which the loading of the cable is made. So the optical unit is more or less hanging on the metallic strength member. And there's another type, lashed cable. It's a non-metallic cable installed on a separate suspension catenary and held in position with a binder cord or special preformed special spiral clips. So these are in general the types of cables we see for aerial applications. Any questions on this? Then, Maronized terrestrial cables. This kind of cables are underwater optical fiber cables based on a conventional multiple fiber terrestrial cable core protected to withstand the marine environment. These kind of cables are designed for unrepeated applications, so hence without the need to carry electrical power, and is tested for use in non-aggressive shallow water. So we do not intend here to build up ocean crossings. These are only intended for shallow water applications like lake crossings, for instance. As said before, here you see the kind of applications, river crossings, lake crossings, fjords, etc. These kind of cables must be able to withstand during their lifetime the water pressure that acts upon them, so up to a water level of about 100 meters deep. And the cable should be designed with sufficient strength to withstand all pressure it is intended to encounter during the storage at and the laying from a cable laying vessel. Then of course some forces are acting on that cable, and possibly if at some time if the cable has to dig up again and should be for repair purposes, if you dig up the cable, then again forces are acting on the cable, and the cable should be designed in such a way that it can take care of that. Any questions on this kind of particular cables? Examples you can see over here. You see the examples also in your book. You see here an example of standard core structure. So in the center, you have the optical fiber unit containing the fibers. And you see in particular here the armoring, metal armoring around that optical core, making the cable sufficient in strength to withstand all the forces acting on the cable during installation. Similarly, also here on the left hand, reinforced core structure. You see here the armoring around it. And again, the optical unit in the center part. So in fact, we have here a double strength member. We have a strength member in the central part and armoring in the outer part of the cable. Okay, any questions? Yes?
If you're constructing a terrestrial network, why would you use this type of cable if you're not going through or crossing like lakes, or would you be able to use this kind of cable then?
Well, again, this is a very special application, of course, and normally if you have only land crossings, you won't need this kind of cables, that's clear. But for instance, if you have in your country a traject in which you need a terrestrial network, but somewhere you have to cross a river or a lake, then you can combine that particular section with this kind of cables. For instance, if you look into European explanations, we have in Norway large fjords. If you have to cross those fjords, you can use this kind of cables. Another explanation is in Finland. In Finland, you have a lot of lakes, and because it's difficult also always to avoid those lakes, sometimes you have to cross them, and then you can use this kind of cables as intermediate sections crossing that particular water barrier. Okay, thank you. Any more questions? The real deep sea applications are submarine cables, and in this case the cable and the cable jointing boxes, cable couplers and the cable transitions should be handled with safety when they are installed first on a cable laying ship. Of course, also during the laying procedure, if the ship is slowly moving, then the cable will be withdrawn from the cable and laid down on the seabed. And repair operations. Sometimes you have to dig up a submarine cable when it is damaged, then you have to pick it up again and again. The cable should be designed in such a way that it can withstand all those high forces. It should be capable to withstand very deep depths, as you can see, even to this kind of 8,000 meter depths. As said before, it should withstand multiple passages over the bow of a cable ship. When the cable is laid down, the cable is coming from the main part of the ship and bent over the cable bow, so there is a bending acting on that position, and the cable should be able to withstand the forces acting on the cable there. Yeah.
Sorry, can you go back on the point 4.1? Okay. Yeah, here you can see two types of cable, aerial cables. I see the LSS and the SS.
Yeah, that's the one we have seen in the first picture.
This is the SS.
This is ADSS.
And there is SS. And what about the OPGW?
Well, that is a general name for OPGW. It's a general.
It's a part of the OPGW. Yes. Yeah. Okay, so meaning the LSS and the SS.
Okay, now I made a mistake. Sorry, I made a mistake. In OPGW, optical power kind wire, then you take in general the Earth's connection in the optical power line. You can replace one of those smaller metal tubes by or metal strain members by a metal tube containing the fiber. I don't have a picture of that in the handbook here. So yeah, indeed. So usually the ground wire is built up out of a standard collection of metal rods, so to say. And what you can do then is to replace, yeah, exactly. Another construction is indeed to take the center part of this OPGG and there you put in your fibers and surround it with the metal wires forming the ground wire. Unfortunately, not everybody can show that here. Yeah, it is possible. Okay. Yeah. Do you want to show it? So indeed, this is a special version of an aerial cable, being part of a power line, and usually the ground wire is then used for adding some fiber elements. It can be either a central construction, as we've seen before, in which the fibers are added, and then the metal rods are standard around that. You see here different possibilities. Sometimes also the metal rods can be replaced by a metal tube in which the fibers are placed inside this tube. So there are different possibilities for building up OPGW constructions. I do not exactly know why in ITU we haven't mentioned this particular construction. I'm not a regular member to the cable group, so I can raise that question maybe later to our next tutor. Maybe an addition for the next edition of the handbook. But this is indeed a good to show that also this is an application example of an aerial cable being part of a power line construction. Okay. Do you want?
Sorry, I should add something on this one. For power line construction, normally you have 3 phases for power, carrying power, and then you have the protection wire. Before it was used a copper, aluminum and copper for protecting the transmission line. And with this technology, inside you are adding the fiber, and then you should transport some data through the line using the optical fiber, and at the same time you are protecting your line. Okay, thanks.
Again, I apologize a little bit because I'm more a fiber maker than a cable maker. So. Okay, any more questions on aerial cables? We have already discussed Maronized cables, and we were now on the edge of submarine cables. What is indicated here further is that the cable should be repairable, and the time to make a cable join on board of a ship during a repair in good working conditions should be reasonably short, because that's, of course, often these lines are very expensive. They're carrying a lot of capacity, so the restore of a submarine cable should be done as fast as possible to have the line working again. When there is a break on the sea bottom, the cable is in such a way protected that water should not go into the cable construction over a longer length than, for instance, 1 kilometer. So there are protections inside the cable on that aspect. Particular cable constructions are indicated over here. You can find them also in your handbook. There are different forms, a lightweight cable construction over here, heavier construction over here, a copper tube surrounding it, and of course you see a lot of armoring of metal wires to build up a very strong cable design. In this case, you see even a double armoring system. In the inner part, you see an armoring of metal rods, and an outside secondary armoring, giving additional strength to the cable construction. You can understand that if such a submarine cable is being introduced into the water and is hanging there for kilometers inside the water, extremely high forces are acting on the cable. So therefore you need, in such cases, very heavy armoring to protect the inner part and not being strained too much. Okay, so questions on submarine?
Yeah, thank you. About the time to repair the cable, the word reasonable is very generic. Do you have a practical figure that we can refer to?
Difficult question. I'm not so familiar, in particular in this kind of subject. I don't have a clear answer to that. I can imagine that this should be done in days instead of months, so to say. You cannot go with a ship and keep it on that position for a long time. I imagine it is a very short time, meaning expressed in days, I assume. But I don't have the clear answer to that. I apologize. Okay, I mentioned already a very special application of fiber to the home constructions, taking care of the sewer pipe, which are present in many of the large cities. And this is already an infrastructure which can be easily, in general, easily obtained, and in which you can lay down your cables. Of course, you have to take care then for the special cables in that environment that you have to take care of the special temperature variations. You should, of course, take care of the rodents which are present in the sewer pipes. You have to take care of possible chemical agents which are flowing through the sewer pipe. You should take care of the high humid environmental, which may induce moisture permeation. So therefore your cable should be designed, and the possibility the fiber cable is soaked in water. Also there, it requires special attention for your cable materials, your cable sheaths. The cable constructions are indicated in your handbook in two ways. I do not go in much detail. You see again, there's a lot of armoring around it. It's of course a somewhat aggressive environment, the sewer environment, but it's being used and installed in several cities. For instance, in Europe, I know in several cities like Paris, in Vienna, this kind of systems are being installed for fiber to the home applications. Any questions on that? Riser cable for inside a building applications, so for instance multi-dwelling applications, meaning you have a large building with a lot of dwellings in which people are living, and you have to go and connect all those different building blocks with a basement where the fiber are entering. So optical fiber networks have been entered buildings in view of the ongoing demand of fiber to the home networks, fiber to the home as said. In this kind of applications we need indoor cables, so we don't need a very strong cable, because inside the building you have not such a high forces acting on the cable. Custom premises require some form of flame retardancy, including the use of low smoke zero halogen sheets. So these are the typical applications if you are inside building. The cable is constructed in such a way as to afford some degree of protection when flame propagation is present. So in case of fire, the flame should not be guided through the cable. That's important, and also to have a low smoke emission, because people are living in this area. Focusing on multi-dwelling units, the vertical access to buildings of several floors requires new type of cables, and this is called a new category riser cable. And for the vertical cabling, I will show you in a moment, mid-span access is made available to extract fiber or bundles of fiber on each floor, depending on the building construction. That is explained over here. You see here that the vertical riser cable is being installed. And for instance, if you want to take out of this cable certain portion of fiber, which had to be at this distribution point guided to the users at this floor, you make a connection at the next higher floor. You make an opening in the cable sheaths. You can cut down parts, those fibers which need to be pulled down, and you can then use these fibers for the installation on this floor. So that's the typical, one of the applications being developed in particularly for this kind of riser cables. And of course you can repeat it for next higher floors for the remaining fibers in the cable. So this is a very easy way of installing. In some cases even you can use the same fiber without additional splices. You can reduce the number of splices if this fiber can go directly to the next user. Okay, this is the clarification. Some cable constructions, you see here already mentioned the micro-module cable in some form. And you can also here have tight buffered construction in a form. In all cases you see that in these cases you see that the stanch member has been moved to the jacket material again to make very compact cables. Okay, this is in particular for those areas where fiber to the home is going very, very rapidly. Europe, US, Asia. I propose that we stop here. I was at the position of section 5, which is completely at the end of chapter 2. It deals with optical cable test methods. And like I also indicated for the fiber section, the testing of cables is outside the scope of this handbook. Information on cable testing can be found in a special document called Supplement 40, which you can find on the ITU site. It's Supplement 40 to the G series of recommendations, so it's related to the cabled fiber. And also you can find it in the relevant ITU-T L series recommendations. And on that point I come back in a moment. Again, all those recommendations you can find on this link. In addition, also in ISC, the other international standardization organization, you find a lot of cable tests, and they can all be found in a document indicated by ISC 600794-1-2. So all the main cable testing is available in this document. There's one drawback: ISC documents are not for free. So you have to buy them. Okay, as an annex, I have added here some more information. So this is not part of chapter 2, but I wanted to draw your attention to a couple of L-series documents which are and have been developed by study group 15, in particularly question 16, which is involved with cable construction and cable installation. For instance, I mentioned you a couple of these documents. The first one I like to mention is document L10, which is optical fiber cables for duct and tunnel applications. It was raised in 2002, and it describes characteristics, construction, and test methods for optical fiber cables for duct and tunnel applications. So if you want to go deeper into this kind of document, and certainly the duct cable is an important one, you can address that and find information on that in document recommendation L10. Another one is document recommendation L26. This is an optical fiber cables for aerial application. It's also created in 2002. And here you found all the characteristics of those applications, construction, test methods for optical fiber cables for aerial application. However, it does not apply to what was mentioned this morning, OPGW cables. Then recommendation L43. This is a document for optical fiber cables for buried applications. Again, it is from 2002 when it was created first. And it describes the characteristics, construction, and the test methods for optical fiber cables for buried applications. And L58 is a document showing special needs for access networks. It has been created in 2004, and it gives characteristics, construction of optical fiber cables for access networks. It's added here, such cables are required to have some additional performance characteristics, e.g. high fiber count, mid-span access, compared to cables for trunk systems. We have seen those particular cables for in-building applications where you have mid-span access, and that is described in this document L58. Another document is recommendation L59. It's optical fiber cables for indoor applications. It's a rather new one. It's created in 2008. And here, this document is focused on all aspects of characteristics, construction, and test methods for cables used for indoor applications, aiming, of course, to fiber to the home developments. Recommendation L60 gives information on optical and metallic hybrid cables. Again, it gives such a cable is a cable which contains both optical as well as metallic wires for telecommunication and or power feeding. Recommendation L67 is for small count optical fiber cables for indoor applications. It is from 2006, so rather new. And this recommendation describes characteristics, construction, and test methods for small count optical fiber cables for indoor applications containing one or two optical fibers. So indoor optical cables that contain 3 or more fibers are described in L59. So there's obviously the cable colleagues found it important to have a separation between small count fibers, cables, up to 2, and more than 2 fibers. Then recommendation L78, it's optical fiber cable construction for sewer duct applications. I showed you already that is one of the possibilities to install in large cities in the sewer system some cables, because that infrastructure is already available and can be used for fiber to the home. You need special cable design for that, and that is described in this recommendation, construction, test methods for sewer ducts and drain pipes. Then recommendation L79 is an optical fiber cable element for microduct blowing installation applications. It's dating from 2008, so also reasonable young document. It describes the characteristics, the construction and test methods for microduct fiber units and microduct cables to be used with the blowing installation technique. There's also a new technique, and later in the course you will find that back, how that is going on, blowing techniques. Then question 16 has also developed the following L-series recommendations for different applications. This is real new work as you see, it's from this year. Recommendation L87 is optical fiber cables for drop applications, supporting again fiber to the home development. This recommendation describes the characteristics, the construction and test methods for optical fiber cables for drop applications. And optical fiber drop cables are used to connect customer and optical access networks. Access points may be located in both outdoor and indoor depending upon the access network configuration. And when access points are located in outdoor, optical drop cables are exposed to both outdoor and indoor environments. So this document really focuses on the applications of fiber to the home and particularly the last portion of the network, the drop cables. L82 is also a very new one from this year. Optical cabling shared with multiple operators in buildings. There's also a development that in certain countries, the regulators require that multiple operators should have access to such networks. And this recommendation refers to the single mode optical cabling in new and in existing buildings. The first part of the section explains the main constraints of a common optical infrastructure for more than one, so several operators, offering fiber to the home services to customers in the same building. We see a lot of this kind of discussions in European countries, for instance. That brings me to the end of my presentation on chapter 2, cabling. So I can raise again the question, do you have any question on the subjects I have been spoken about today? We have seen a lot of different aspects. Certainly also in the discussion of yesterday, which we had, and also the first part this morning, the different types of fibers. I think this is a difficult subject, and I refer again also that we come back on this issue when the tutors on systems are here next week, so that we continue that discussion. So if there's any reason to go back into the material we have been shown, please raise your hand and we can have a further discussion on that. Yeah.
I want to know the difference between this fiber cable for duct and the fiber cable for buried application, buried and duct application. L10. Yes, L10 and
Okay. Buried cables are which are laid down directly in the ground, so in the soil. While in duct applications, you have a kind of a duct that can be a stone grid or a cement grid in which you can lay down your cable. A kind of, yeah, you can say the kind of pipes. It can be cement, concrete installations in which you can lay down your cable later. So there's a distinction between duct cables and directly buried cables.
I'm asking if the fiber, ground wire fiber, is it different the blade cables?
You have seen that in ITU we have not taken care of the OPGW. I do not exactly know why. Maybe Attilio, do you know the reason why OPGW was not incorporated in ITU?
Thank you, Chair. We have some information about the installation of OPGW and also general recommendation for this kind of cable. Then tomorrow we will see some part of this, mainly related to installation of this cable.
Again, I apologize. I'm not following so much the cable discussions in ITU. I'm focused more on the fiber sections. So I cannot give you a complete answer why OPGW is not inside the ITU system. So if someone else maybe has the answer, I apologize for that. Okay, I like also to introduce you to the next tutor for tomorrow and Thursday, Mr. Attilio Rajani. He will be your tutor for the next coming days.
Together. I'm really glad to be here, and I will deal with this subject related to Chapter 3 and Chapter 4 and part of Chapter 10. Then we will deal with installation of cable and also some passive components used in this kind of network, and also some part of the maintenance aspect related to the optical fiber cable. Then I appreciate all this interest in this subject that we have been devoted so many time just to prepare this information. I'm very glad to share with you. Thank you.
Okay, thank you very much, Attilio. Well, this brings me then, I think, at the end of this presentation today. The question is how we fill in the time then up to the minister will arrive. Let's make a break now and wait for his arrival. If there's anything you want to raise at this moment, please feel free to raise your hand, and we can have another discussion on some of the subjects we have been talking about. Thank you. Oh, there's a question.
Thank you. I have a small question on directly buried fiber cables. What the recommended depth of their directly buried underground cables? Because I could see some operators use 1.2 meter, and the others are planning to the likes of 1.5. What the recommended depth on it?
Yeah, it's maybe an aspect of cable installation, and I don't know, Attilio, whether you have an answer to this. It has to do with cable installation. How deep should you place a directly buried cable? Is that addressed in the handbook?
Thank you, Karen. Most usually values are around 1 meter, and some place when we are more comfortable with some earth movement could be a little short, but most of the values used are between 70 and 7 centimeters and 1 meter. Thank you.
Any more questions? Job cable, you mean? Job applications? That is usually the terminology for the last portion of the network. This is the last portion of a fiber to the home network, and it's describing often the in-building cabling. Often that is called job cable. Yeah. Okay, I see no other questions going on. So I propose then that we break now and we wait for the arrival of Minister of Telecommunication. Yep.
Maybe we can introduce the second trainer. You can introduce him for. Yes? You don't want to take the floor to say a few words? Yes? Oh, sorry.
In a new version. And the chapter 3 deals with optical cable installation, and as other recommendation related to this subject, the idea is to have quantity amount of useful information, and I try to put emphasis in some technical aspects. This chapter is divided in two clauses. The first one is the biggest in the chapter, is cable installation method. The second one, just a reference, is some points about safety in service protection and location. Most of the time we'll expand in the first one, cable installation method. And there is a lot of cable used in optical communication networks. Then the first one will be the optical cables in underground ducts. And the second one will be optical cable with trenchless technique. The third one will be optical cable with mini trench technique. And after that, optical cable with micro trench techniques. After that, we will deal with aerial cable, buried cable, cable in tunnels and on bridges, optical fiber ground wire cable, UPGW, and optical cable along railways, cables in sewer ducts, Marionized and submarine optical cables, and indoor cables. Some of these are more well understood and more well treated in the recommendation. Some of these are less detailed, but we will discuss specifically each one. In safety, service, protection, and location, we have, as the title says, the three topics: safety, in service, protection, and location. As we have different kinds of cable, every one of these has some specific strength limit and needs special care. And the idea is to take care of this cable without exceeding these characteristics, this limitation. Some damage that we can put in this cable, they are caused by overload during installation. And some of these may not be immediately apparent, and some takes several years to cause the problem in the fiber. Then it's why that's in the minimal detail, this recommendation must be followed. And bending, there's always a problem in fiber and also in optical cable. Then the bending, especially in installation, it needs to be taken account. This way, during the installation, the optical fiber must be protected with respect to excessive strains that can be produced actually or bending. And these optical fiber cables, it should be installed with the fiber as near as possible in a strain-free condition and ready for splicing. There is a lot of methods and practice that can be used in the handling of optical fiber cables. In these methods and practice can affect their long-term transmission characteristics. Even though we didn't notice at the first moment, they can cause some damage in cable from days to years after it's been used, if you use the wrong technician. Then this way, all the people involved with this operation, involved with the installation of a fiber cable, should be aware of this method and know about the correct way to use, to deal with this cable. And of course, some of this information deals with a lot of detail, and we are always trying to understand more this and know how to protect the fiber against this kind of damage. And in particular, the criteria of minimal bending, it's important to be followed, because bending could cause the increase of the failures that the fiber has, especially at his surface, and each increase of the dimension of this failure could be part of the effect that will cause the reduction of the lifetime of the cable. And all these points, they are controlled in a certain way when we decide the characteristic of the cable, and this must be taken account when we install every kind of this cable. And the first one we will do will be the cables in underground ducts. And the first important point in this kind of cable is related to root consideration and the conditions of the soil, the condition of the place the cable will be put in contact with the duct. The geometry of the duct is important. Then it's important to look to the distance of pulling and look what will find, the cable will find in the way to reach the other side of the duct. If we have excessive curvatures, or if the duct already contain cables, or if the duct has some abrupt changes in direction, all these conditions must be part of the preoccupation of the people that are involved with the root. And one way to understand quantitatively this situation is calculating the maximum cable tension. Then this maximum cable tension must be calculated, consider like an example what we have in figure 3.1 at the handbook. When we have a lot of sections with different characteristics, then we can see here that we have some points of control, and we have all information about these points relating to the geometrical effects, the inclination, the deviation, and considering this and some math, we can find a way to obtain this tension, accumulate tension. Then we can go first at the point A and do all the calculation to the point G and find in kilonewtons what will be the tension that the cable will suffer when it's pulled. It's just an example, but I think can give you an idea what can be done as we have the right information about the ducts. Then we need this kind of information: the distance, the inclination, radius, the change in directions. We need all the information and also some information about the cable, and we have all information about the coefficient of friction between the cable and the duct. And of course, this is assuming all the ducts are clean, and even if it's necessary, it's possible to put a kind of lubricant and help the way the cable will suffer. If we have more than one cable in each duct, we need to consider this as an aggravant of this situation. And generally, they are used factors to multiply this cumulative force tension if we have more than one cable, or if we have a lot of cable, like 4 to 9 cable. Doing this, we can realize what will be the tension that the cable will suffer during pulling, and compare to the values specified by the manufacturer. If we are reaching some points just near the values that limited the the use of the cable, we can do some arrangements. The more general way is to change in some place the planned route. If these force are near the maximum force allowed for that kind of cable, we need to maybe find another way to the cable or change something in the way. And again, this kind of table could be very useful to know what's the tension in each part, each section of the way the cable will be, and sometimes change just some part of the section, reduce the tension, and allow the cable could be installed in the same situation. Any doubt about this question? The main message is take care with the tension will be applied to the cable, and take care of the bending the cable can suffer, and the way from the first point you have the cable and the last point you have the cable. Considering this situation, sometimes it's useful to use some methods to protect the cable of tension higher than we can expect. If we look at that figure, we can see the cable drum and all the way the cable will pass, and in the other way we have some equipment that pull the cable. First, there is a passage of rope that is connected to the cable, and after that, this rope just pull the cable in the way. There are several ways to try to avoid any problem with this operation. One important way is to put device in the primary or intermediate switch that can consider and measure the force, the tension that are applied in the cable. Then exists a lot of mechanisms that can be put in. Here we have some example. Here we have an intermediate puller. Here we have a fusion link. And here we have a tension controlling system. This figure also shows the use of lubricator. Then the idea is to combine these elements to make the way of the cable easier. Then the lubricator is responsible for reduce the friction of the cable against the duct. Some intermediate puller could put some additional movement and help the passage of the cable. They are more important when we have a long length between the initial and final point. The fuse link is a kind of device that could stop the pulling action when certain level of tension are reached. Then it's similar to the other kind of fuse. He just stop the movement if some level of tension, high tension, is reached. The tension control system is important, especially when the people that are contracting the operation of installation wants to have some historical information about that cable. Then if there's some strong tension, strong force, higher tension applied during the installation, sometimes or most of the times this not appears in optical measurement. Then if the company has some records of this tension applied, it's easier to understand if some problem could be caused in the lifetime of the cable because of the installation. And when we consider tension, these are the main elements. But when we consider bending, it's important to look carefully to these points where cables change in direction. Then it's important to have guides, special guides, mechanical guides, just to give the radius of curvature that we expect to be higher than the limit of the cable. Then if we have the correct guides, and if we have some intermediate puller, if we have records of the tension controlled, most of the time this operation could be successful and the cable could be installed without big effect in his mechanical properties, because all that could be affected most of the time when we have good optical information about the cable installed, what we can have also is information about mechanical situation of the cable. All of these devices that are most of the time well applied, they can establish a good condition for the cable installation, and this is one of the reasons. This is one of the most used kind of installation of optical fibers.